Chapter 6 is all about roots. Not just like roots of equations, though. It's roots like square roots, third roots, fourth roots, fifth roots, what we call nth roots. Find nth roots. The letter n just means some number. So it could be the 20th root, or the 5th root, or the 2nd root, or the 3rd root. We're going to be doing all of that. Well, maybe not the 20th root. Though we could. Once you learn what that means, then you can find any root you want. To do that, we're going to have to review the properties of exponents that you learned in Algebra 1. This little table right here, this little chart, is Algebra 1 stuff. You already know how to do this. You learned it in Algebra 1. So we're going to review it because probably you forgot some of it. Before we get into it deeply, we need to review these properties. So first of all, I'm going to take this one first. A to the m times a to the n is a to the m plus n. What that's saying is when you multiply like bases, what do you do to the exponents? You add them. So like for example, x to the 3rd times x to the 5th becomes x to the 8th. Now the reason for that is x to the 3rd is x times x times x. You've got to remember that exponents are a shorthand way of writing repeated multiplication. Just like multiplication is a shorthand way of writing repeated addition. Right? Okay. Like if I did 3 plus 3 plus 3 plus 3 plus 3, what I'd have is 5 times 3. That's repeated addition. This is repeated multiplication. So x to the 3rd turns into x times x times x. X to the 5th is x times x times x times x times x. And what are we doing to those? Well, we're multiplying them together. So what I have is x times itself 8 times. And that's why we wind up with x to the 8th. And now clearly I can see that 3 plus 5 is 8. So that's why this property right here, a to the m times a to the n equals a to the m plus n, is that property. When you multiply like bases, you add the exponents. Now, this one right here, if I'm dividing, no, not this one, sorry. This one. If I'm dividing like bases, what do I do to the exponents? I subtract them. So, for example, if I had x to the 5th divided by x to the 3rd, I should wind up with what? X squared. Now, if I write this out like I did with the other one, then that's x times x times x times x times x divided by x times x times x. Well, what happens with 3 of those x's? Yeah, they're fancy ones. X divided by x is fancy 1, it's gone. X divided by x, fancy 1. X divided by x, fancy 1. So what's left in the denominator here? It's not 0. It's 1. The number in front of each one of these letters is a 1. 1 times 1 times 1 is 1. We wind up with x times x divided by 1, which is what? X squared. So now clearly I can see that 5 minus 3 is 2. So that's why this property right here, a to the m divided by a to the n, becomes a to the m minus n. You subtract the exponents. When you divide like bases, subtract the exponents. The next one I want to do is this one right here, a to the 0. We talked about that in the last chapter. Anything to the 0 power is what? 1. Well, here's why. There's actually a couple ways you can see this for sure. But on this problem right here, if I have x times x, so if I have x to the 5th divided by x to the 5th instead, then I need another times x and another times x here. So what winds up happening now is gone. Gone. What am I left with? 1. Well, what is x to the 5th divided by x to the 5th if I use this property right here that I just learned? Yeah, we subtract 5 minus 5, which is 0. So x to the 5th divided by x to the 5th we know is x to the 0. And we also know that if I write this out, I wind up with just 1. So therefore x to the 0 must be equal to 1. So anything to the 0 power now is 1, except for if you have 0. Anything else, anything to the 0 power besides 0 is 1. When a equals 0, what happens? It's a good question. Type it into your calculator. Type 0 to the 0. Undefined. Why? If you follow this right here, 0 to the 0, like if I had 0 to the 5th divided by 0 to the 5th, 0 to the 5th is still division by 0, and that's why it's undefined. Okay? So any 0 to the 0 is undefined. That's why the calculator gave you that. 0 is neither negative nor positive. We can treat it like a positive. We can treat it like a negative. It doesn't matter because it's just 0. 0 to the anything power is still 0 because it's 0 times itself that many times. All right, so now we know that one and that one. We know this one. How about AB to the n? Let's do this one first. A to the m times n. So what that means is, here's an example. Like if I have x to the third, let's make that x squared, and let's make it to the third power. That's basically what a to the m to the n means. Well, anytime I raise something to a power, what that means is I'm multiplying it times itself this many times. So what I'm doing is I'm taking x squared times itself 3 times. So if I write that down, x squared times x squared times x squared, what do I have? Yeah, x to the 6th. Because now I have like bases that I'm multiplying together. And I already know that if I multiply like bases together, I add the exponents. So 2 plus 2 plus 2 is 6. So x to the 2nd to the 3rd becomes x to the 6th. What happened? We multiplied the exponents. So that's what this one right here is saying. A to the m, then to the n, is a to the m times n. You multiply the two exponents together. So what I'm going to say is when you raise a power to a power, you multiply. You get a to the mn. So for another example, if I had x to the 3rd and I raise it, oh, sorry, no parentheses there, to the 4th power, I'd wind up with x to the what? Good. X to the 12th. All right, so now we know this one. Now this one we dealt with in the last chapter, section 7. AB to the n. Both of these are being raised to the nth power. Well, let me do an example. Let's go x, y, and let's raise that to the 4th power. Actually, let me go one better. Let's go x times y squared and raise that to the 4th power. Well, what that means is I have x, y squared times itself 4 times. Now, by the commutative property of multiplication, I can multiply this any way I want, which means I can go x times x times x times x, which is what? X to the 4th. And I can go y squared times y squared times y squared times y squared, which is y to the 8th. Technically, what I have is y squared times itself 4 times. And we just learned this rule right here. Anytime I have a power to a power, I multiply. And I wind up with y to the 8th. This is the long way to write out this property right here. As long as everything's being multiplied together, as long as it's strictly multiplication here, and all of this stuff being multiplied together is being raised to a power, then I can send that power in and attach it to each one of those exponents. Technically, that's an a to the 1st and a b to the 1st. Well, n times 1 is n. N times 1 is n. Up here, I had a 1 and a 2. 4 times 1 is 4. 4 times 2 is 8. So if I'm raising stuff that's all being multiplied together, I can apply this rule right here to each of those terms. Basically, it's kind of like distributing the exponent in. Now, this is not, let me pick a really ugly color here. If I had that, does that mean that I can take this 2 and send it in? No, you cannot do that. What do I have to do in that case? This would be a FOIL problem. Yeah. What's the difference between the way this problem looks and the way this problem looks? Yeah, the addition sign in between. This is 2 terms being multiplied together, or being added together, sorry, and then raised to a power. That is not the same thing as two things being multiplied together and raised to a power. So be careful of that, because those types of things will pop up from time to time. You cannot send exponents in unless this is the case that you're dealing with here. All right, so we have this one, we have this one, and this one. We have this one. Similar to what we just learned, a divided by b to the nth power becomes, it's like I send the n into the top and the bottom. The reason that that one works, let me get rid of this color because it's terrible. The reason that one works is if I have like x to the first divided by y squared, kind of using the same idea here, and I raise that to the fourth power, well, what that means is x divided by y squared times itself 4 times. And how do I multiply fractions? No. If I'm adding fractions, I need to common denominator. If I'm multiplying fractions, I just multiply straight across. So x times x times x times x is x to the fourth divided by y to the eighth, because I'm adding these exponents together. Here I'm adding these exponents together as well. 1 plus 1 plus 1 plus 1 is 4. This is y to the eighth. Well, what happened? I started with x divided by y squared, and I raised it all to the fourth power, and I wound up with x to the fourth divided by y to the eighth. It's like I took the exponent and sent it in and multiplied the two exponents together. X to the first times 4 is x to the fourth. Y to the second times 4 is y to the eighth. That's what this property right here is telling you. It's sort of a blend of two properties that we've already learned. All right, so now we know that one. What's left? This one. This says a to the negative some number is equal to what? 1 over a to that number, but now the exponent is positive. Now the reason that works, let me get rid of this since we don't need it. Work, thank you. The reason that that one is true is this. I'm going to use the same type of example as I did right here to show you this one. Let's go x to the third divided by x to the fifth. If I'm using this property, what do I wind up with as an answer? X to the what? I got to do subtract, right? So 3 minus 5, what is that? It's negative 2. So this gives me x to the negative second power. Well, if I write out x to the third, I have x times x times x divided by x times x times x times x times x. Now if I do like what I did here, I can form a bunch of fancy ones. Here's one, here's another, here's another. What's left in the numerator? What's left in the numerator here? 1. Divided by what's left in the denominator? X squared. So we know that x to the third divided by x to the fifth gives me x to the negative second power based on this rule right here. But when I write it out like this and form all my fancy ones, I wind up with 1 over x to the positive 2. So therefore, x to the negative second power is 1 over x to the positive second power. And that's where this property right here comes from. Something to whatever negative power means move it to the denominator, put 1 over it, make the exponent positive, and you're done. So like if I had y to the negative 10th power, that would turn into 1 over y to the positive 10th power. We move it to the denominator. We'll see this in a little bit, but if I had something like 1 over y to the negative 10th power, then this one is going to result in moving it to the numerator. Basically, you move it from wherever it is to the other side of the fraction, from top to bottom or from bottom to top. The reason that that one's the case is because I still have that 1 over. This y to the negative 10th power is 1 over y to the positive 10th. If I do leave it, change it, flip it on this, then I have 1 over 1 times, now I got to flip this, y to the 10th over 1, which is just y to the 10th. So that's all your rules. We've now covered all 7 of them. These are the properties of exponents. You learned every one of them back in Algebra 1. You need to know them by heart and be able to use them instantly, just as instantly as you know how to add 2 plus 2 in this chapter. The more you are comfortable with these, the better off you will be in this chapter, because these do not go away. We use them every single day in every single section in this chapter. Got to know them. All right, so let's work on these 3 examples right here. We have 5a to the 3rd times negative 3a to the negative 4th. There's a lot of ways that you can go about doing this. First of all, I see this a to the negative 4th, and I know that that negative exponent means that I have actually 1 over a to the 4th. I see like bases here, so I know that when I multiply like bases together, I need to add the exponents. I see numbers sitting here like this. And all of this stuff is being multiplied together. And I know because of the commutative property of multiplication, that means that I can multiply in any order that I want. To do a problem like this, you are using all of the properties of exponents. I can rewrite this as 5 times negative 3 times a to the 3rd times a to the negative 4th, if I want. Just because this is the very first problem in this chapter, that's how I'm going to do it. So that you can see that the result is, I'm going to take 5 times negative 3 and get negative 15. And then I'm going to multiply these like bases, a times a, but it's a to the 3rd times a to the 4th, which means what am I going to do with my exponents? I'm going to add them. So 3 plus negative 4, which is what? Negative 1. So I wind up with negative 15 times a to the negative 1. Now my answer has to be rewritten because I'm not allowed to have an answer with negative exponents. So this is an a to the negative 1st power. What happens? I need to put it in the denominator. It's currently in the numerator. So I have to move this a to the negative 1st to the denominator. What do I do with this negative 15? Is there a negative exponent on that negative 15? No, that's a negative sign, not a negative exponent. Don't get confused with negative exponents and negative signs. That negative 15 is just a negative 15. It's being multiplied times an a to the negative 1st power. This guy right here alone is 1 over a to the 1st power, or just 1 over a. So what we have right now is negative 15 times 1 over a. And when I multiply fractions, I multiply across. So I wind up with negative 15 divided by a, and that's my answer. Now I went a very long way on this problem. I went a long way around to go from start to finish. You don't have to do this step. What you need to realize is that I'm going to multiply, since this is all multiplication, I'm going to multiply my numbers together and get the negative 15. Because I have all multiplication and I have like bases, I'm going to add these exponents together and get a to the negative 1st. And that a to the negative 1st means it needs to go in the denominator. As you get more experience with these problems, you'll be able to go from here to here instantly. It's just a matter of remembering all your properties of exponents. If you don't remember the properties, then you're going to have to take a little bit longer to get there. For example, on this one, here we have a bunch of stuff being multiplied together. I see a negative exponent here, and I know that that means that that thing lives in the denominator somehow. But I'm raising all of that stuff to an exponent. Raising all that stuff to an exponent means that I have exactly what I see here multiplied times itself this many times. So I'm going to write that out. Negative 4, x to the negative 3rd, y to the 5th times itself. Negative 4, x to the negative 3rd, y to the 5th. Now that I have it written all out, just like I did over here, I'm going to multiply my numbers together, and I'm going to multiply my like bases together. So negative 4 times negative 4 becomes positive 16. X to the negative third times x to the negative third becomes, I heard x to the ninth and I heard x to the 0, but it's actually x to the negative 6. When I multiply like bases, I add the exponents. Negative 3 plus negative 3 is negative 6. And then y to the 5th times y to the 5th is y to the 10th. Good. All right, now I'm not done because I have to simplify this. I can't have an answer with a negative exponent in it right here. So what do? This guy right here with the negative exponent is currently in the numerator. If I put it over 1, I have to move it to the denominator. So my answer is going to be 16. The x to the negative 6 goes to the denominator and becomes x to the positive 6. The y to the 10th does not move. It stays in the numerator, and there's my answer. If I had any fractions to reduce, I would reduce the fractions. But I don't, so that's my answer. That's the long way. If you remember all of your properties of exponents, then you know that when you raise stuff to a power and it's all multiplication, then you can treat this as a distribution of the exponent to each of these. So what I have here is negative 4 to the second power, which is positive 16. I have 2 times negative 3 because I'm raising a power to a power. Negative 3 times 2 is negative 6. So I have x to the negative 6. X to the negative 6 tells me that lives in the denominator. Y to the 5th times y, or times 2 becomes y to the 10th. That lives in the numerator. Knowing those properties of exponents saves me all of that extra work. And I get to the answer in one move. For this last problem, I'm not raising powers to powers here, so that's nice. But what I do have is a bunch of like bases being divided. How do I divide like bases? I subtract the exponents. So what this actually says is 4 over 1 times a over a to the 5th times b to the 6th over b times c to the 3rd divided by c to the 3rd. Do you agree? If I multiply all this back out, I get the denominator. If I multiply all that back out, I get the numerator. So now we're going to simplify this. 4 divided by 1 is still 4 divided by 1. A divided by a to the 5th becomes a to the negative 4th. B to the 6th divided by b becomes b to the 5th. And then c to the 3rd divided by c to the 3rd becomes c to the 0, or just 1. So therefore, times 1, I don't need to write times 1, so it just kind of disappears. It doesn't go to 0, it's not 0, it's 1. But since this is all multiplication, I don't have to write the times 1. If you really want to, then you can. But now you got to do more. If I didn't put the times 1 in there, you don't have to put it in there. So if you don't put it in there, then you don't put it in there. And I'm happy because it makes me think that you know what you're doing. This is not a good answer here. We need the a to the negative 4th to go to the denominator. The 4 stays in the numerator. We have the a to the 4th now in the denominator, the b to the 5th in the numerator. That times 1 goes away. And I have my answer right here, 4b to the 5th divided by a to the 4th. But if I know my properties of exponents, I can avoid both of those steps that I just did and go straight to the answer. To do that, I'm going to suggest you just draw your division bar. I have 4 divided by 1, which is 4. That's a positive exponent. Positive exponents live in the numerator. I have a divided by a to the 5th, which is a to the negative 4th. That's a negative exponent. So I'll have a to the 4th power, but it's in the denominator. I have b to the 6th divided by b, which is b to the 5th. That's a positive exponent, so it lives in the numerator. And then I have c to the 3rd divided by c to the 3rd. C to the 3rd divided by c to the 3rd is 1. So that's my answer. Know those properties. It will save you lots and lots of time, and lots of work, and lots of paper. So at this point, before we even start the chapter, page 360 is the page just before section 1 begins. 1 through 19 odd, we're reviewing, and that is part of homework assignment for section 1. So start things off. You got like 10 problems. Go.